With the recent discovery of a super-Earth or related exoplanet, maybe even an oceanic world entirely covered in deep ocean, LHS 1140b, orbiting a red dwarf star, a new question comes along with that. LHS 1140b, as far as we can tell right now, is a significantly more massive and dense planet than Earth, but it is holding on to an apparent atmosphere that is leaking helium, and it isn't that large. It's still in the range of a terrestrial super-Earth at about 5.6 Earth masses, or an oceanic one with rock under ocean. Either way, this gets closer to Earth than anything we've seen so far. But astronomy terms can be very vague. When terms like sun-like star are used, for example, the stars involved only broadly act like the sun, but only in certain ways. They need to be stable or relatively so, like the sun. A supergiant star that will live a few tens of millions of years and then explode is not sun-like. The sun doesn't have the capacity to explode at all, and those stars are far from stable. Just take Betelgeuse and how it belched out a huge cloud of carbon. But if you were to see that star close up, it would be a roiling mess rather than a stable sphere. Rather sun-like just means a stable star on the main sequence. This includes type M, K, G, and F stars in general. The sun-like stars can be classified, and indeed they have been. It includes red dwarfs, orange dwarfs, yellow dwarfs like the sun, and marginally type F giant stars that can last as long as 3 or so billion years in the main sequence in a stable manner. Main sequence references what is called the Hertzsprung-Russell diagram, which is a diagram on star characteristics created by Hertzsprung and Russell in 1913. Interestingly, they independently did that from each other, and it classifies stars in stellar evolution using temperature as a basis. It was very good work because it's still in use today. It's over 100 years old, but still holding overall well, a testament to the astronomy of those days. But beyond that, a type M star, a red dwarf, is actually very different than the sun in other ways, as are orange dwarfs, and type F stars are radically different in how much more ultraviolet light they produce. So much so, in fact, that it may be a showstopper for life to ever evolve on the surface of a planet in orbit of one. The term Earth-like exoplanet is likewise just as vague. All it really means is rocky and with an atmosphere in the habitable zone of a star, and does not account for criteria such as whether a planet has oceans of water or what the composition of that atmosphere is. In this sense, you can actually vaguely call Venus an Earth-like planet, even though it's obviously very different in practice. So if LHS 1140b turns out to be a fully oceanic world of a higher mass than Earth, it probably will retain its status as Earth-like, but will not be an Earth analog. In fact, it already isn't. Earth can't hold on to helium, whereas LHS 1140b retains its original helium from its formation. Interestingly, that's actually clean-cut, because there are really only two ways to get helium: nuclear decay and nuclear fusion in a star, or original primordial helium from the Big Bang. LHS 1140b doesn't have the mass to account for the huge amount of helium it has. There isn't enough nuclear decay in its core to replenish it. Thus it has its original helium and demonstrates that red dwarf stars do not always strip the atmospheres off their habitable zone planets. But what will be a problem for LHS 1140b is that high mass. That may actually make for a situation where not only does it have an atmosphere, but maybe a thick, huge one, possibly making it resemble something more along the lines of a small Uranus, with a rocky surface hidden in an envelope of gas than a true Earth analog. Under that thick atmosphere, if it indeed is a thick atmosphere, there may be the ocean. Opaque atmosphere and no land starts looking not very much like Earth in practice. And it probably doesn't have complex life. The upper limit for super-Earths and complex life tends to be set at about 2 Earth masses, though that is highly debated. Some think it's much higher. LHS 1140b is believed to be much larger than that, though microbial life is much more murky. Larger terrestrial worlds might allow for that under certain conditions. A giant ocean planet, if that's what LHS 1140b turns out to be, presents very high gravity. Those oceans are probably extremely calm as a result, but might still offer the option of hydrothermal vents where life might arise. But it seems the lesser likely scenario for how that happened on Earth, with volcanic hot springs on land gaining traction. But another question remains. Eventually, in the search for exoplanets, as our resolution increases, we will be able to detect much smaller planets than we currently can. But whether they can be habitable presents a two-pronged challenge. At some point, a planet becomes too small to hold a major atmosphere of any kind. They become like the Moon or Mercury with almost no atmosphere at all. No atmosphere, no liquid water, no life. But the water part presents a unique challenge because of the solar system's ice shell moons. Those do not need to be in the habitable zone. In fact, none of the ice shell moons are. They can be like Pluto and still have enough radioactive decay going on in their cores to heat a subsurface ocean above freezing, even that far out. This means that basically that type of an oceanic world isn't beholden to habitable zones at all. But they don't have to be moons. You can also have a frozen Earth-sized planet that has a subsurface ocean, opening the way for Earth-sized rogue planets traveling among the stars that may maintain liquid water oceans under ice shells and potentially even ecosystems in the darkness of interstellar and even intergalactic space. The problem is, other than potentially being able to detect such worlds, other than that, we'll never know if they have life unless we go to them and drill. Not likely to happen, even in the far future. So in that sense, all sun-like stars could have ice shell planets and moons because ice is excellent shielding and would block cosmic rays, radiation from the star, basically anything, and provide an oceanic environment for whatever life might arise in those oceans. That's if it's possible for that to happen. This is a question we still don't know the answer to, and the only way we will ever find out is to drill into our ice shell moons and see if anything lives there. If we never find that in any of the ice shell moons of the solar system, then we can infer that it's unlikely to happen anywhere else. But worlds smaller than Earth present other problems for maintaining surface complex life. A good case study here is Mars. It has an atmosphere, but it once had a far thicker, more extensive atmosphere. But the reality is that Mars, being about 2/3 the size of Earth, simply did not have the mass to hold on to that atmosphere indefinitely as Earth did. But at what point between Earth and Mars is there the limit? How much smaller than Earth can an atmospheric habitable planet be? And what conditional situations might change that equation? In a recent study by Michelle Hill and colleagues at the University of California, Riverside focused on simulating these situations, where they simulated planets of varying sizes within the habitable zones of their stars. And one interesting thing they found is that basically the bare minimum actually is Mars. If you go any smaller than Mars, game over. You can't hold enough of an atmosphere long enough to sustain life, at least for very long on the surface of that planet. One oddity here, though, should be said. So in the history of the solar system, the first life we see on Earth occurs at the first moment it could. Earth before the advent of life was just too hot, active, and prone to impacts and so on. So whatever happened to allow life to arise on Earth, it happened immediately once it was possible to happen and gain a foothold here. Another factor here, and this is important for LHS 1140b, is just where the habitable zone of your star actually is. This is directly related to the Hertzsprung-Russell diagram in that the more luminous and hot a star is, the further out the habitable zone is. So for a hotter, more luminous star like a Type F, it's significantly further out from that star than our own habitable zone is. For a star like the Sun, obviously it's somewhere around where our Sun's habitable zone is, and we're sitting within it. This is an interesting hypothetical because if Mars had been roughly the size of Venus and Earth, it's located in the habitable zone, though near the outer edge, and would likely still today hold liquid water, and might actually have been a true twin of Earth, teeming with whatever kind of life might have existed there. As a fun thought, it might have produced a civilization that made the science fiction of H.G. Wells and the War of the Worlds a reality if it had continued to remain habitable. Two inhabited planets within the same system, with unrelated life and intelligence hitting technology at about the same time, is fertile territory for you science fiction writers out there. Wells did not exhaust that one. But back to the stars. So Type K stars feature habitable zones which would be much more tight and closer to the star than our own solar system. Type K are the greatest wild card there is in the search for exoplanets because they are a common type of star, more numerous than our Type G suns class. and are not red dwarfs and do not flare like they do, and live far longer than the sun's lifetime. They will last and remain stable for many billions of years. As far as we know, they are absolutely perfect for life, and the place to be searching for it in the biosignature arena. Trouble is, they also happen to be the hardest type on the list to study because they are bright enough to cause severe glare, with habitable zones relatively close in, which is a compounded problem. Finally are the tiny cool stars, the red dwarfs, such as the one LHS 1140b orbits. These stars begin their lives violent, flaring, but then calm down as they age. LHS 1140b does illustrate that habitable zone planets in such star systems can keep their atmospheres, but only because of mass perhaps, because it may be that a Mars-sized world in such a system cannot, nor can an Earth analog. We just don't know yet, but it is an encouraging discovery and sign. The study showed that a planet that can sustain an atmosphere needs to be about 80% the size of Earth, and in certain circumstances could be as low as 60%. This leads to a somewhat sad scenario, that we live in an extinction universe. We knew that Earth has seen its share of mass extinctions, but not losing an atmosphere. But a planet that sees abiogenesis happen makes it long enough as it can before losing its atmosphere, and then mass extinction occurs might be the rule of the universe, because smaller things in the universe tend to be more common than larger things. There are more Mars-sized planets out there than Earth-sized ones, statistically speaking. It also depends on what gas a planet is trying to retain. Carbon dioxide is probably the star of the show here, as it's more easy to retain because it's heavier than a lot of other gases we see in nature. And microbes, and for that matter plants, can exist within it. Other factors the study includes are volcanism, replenishing, types of volcanic gases in relation to mass, and how stable a star is. And it's possible for planets in red dwarf systems that did get stripped of atmospheres to regain it through impacts and depositing after the red dwarf has calmed down. Also, more work will be done by this team on what effect tidal locking has situationally. But there is a mystery here. Saturn's moon Titan has a thick atmosphere, and it's only 76% the size of Mars. Way bigger than our moon, but not as large as Mars. Yet it's got an atmosphere denser than Earth. It's not completely understood as to how it does that, but it's there nonetheless. It found a path, having to do with very cold temperatures, chemistry, protection from Saturn's gigantic magnetic field, and a replenishment of methane from the liquid cycle going on with the hydrocarbons on the surface allowing for it. I would say that of the bodies of the solar system, Titan presents the most alien world we have, and it's a moon, an arena we have yet to explore or even confirm the first exomoon. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently concerned about barbecue. If you think about it, as far as a classic smoker or barbecue pit, Earth is about the only place in the solar system where you can do that, and possibly may be the only place in the universe you can safely do it. Too much oxygen, and it won't work. Too little, it would take longer, and things may not cook through. If we ever get visited by aliens, perhaps they might say, "Tell us more about this barbecue you have," and we become the barbecue capital of the galaxy. And now I'm hungry, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.